Welcome to OOTO TV, the out-of-the-office investigation from the past into the future of marine navigation and autopilot technology. I'm Commodore Hazard Perry.
And I'm General Cromwell joining you.
Today, our investigation is digging into something that, well, it underpins the entirety of global maritime trade. We're talking about the requirement specification for a marine navigation and piloting tool for both inshore and offshore global navigation. Now, I know it sounds technical, and believe me, it is, but this is the very blueprint for how we guide the largest machines on Earth safely across our oceans.
That's right, Hazard. And let's be clear, we're not just talking about some GPS on a dashboard. We are talking about this incredibly complex web of sensors, software, and of course regulations that allows a multi-billion-dollar vessel to navigate a tiny channel in a storm, or maybe even an autonomous ship to cross an entire ocean by itself. The stakes here are just immense.
All right, let's get into it. We're going to start our journey in a place you can't even see, the invisible world of radio waves that make up what we're calling the unseen digital ocean.
And from there, we'll look at the ship's digital senses, the actual hardware that has to translate all those waves into concrete, usable data.
Next up, we'll step onto the modern integrated bridge to see how the human operator, or maybe the AI, actually makes sense of it all. Then we're going to look to the future, at new threats, new horizons. Everything from sophisticated cyber attacks to the dawn of autonomous shipping.
And finally, we'll pull it all together to really understand how we go about defining the future navigator and what its most essential requirements really are. This is going to be a fascinating voyage right into the heart of modern maritime technology.
So, if you really want to understand modern navigation, you can't start with a ship or a chart. Nope, you have to start with physics. You have to start with the invisible signals that fill the air and the seas all around us, because that's the absolute foundation of how we find our way across the globe today. It is the language that this entire system is built on.
It's such a powerful idea, isn't it, Cromwell? For thousands of years, sailors looked up at the stars, at a visual map. But today, they have to navigate this unseen digital ocean. The entire planet is just blanketed in these signals from satellites and shore stations, and it creates this amazingly complex web of information. The skill of modern navigation has totally shifted from just seeing to listening and interpreting this constant invisible stream of data.
It has, and that shift is, well, it's profound. It means we are completely dependent on the fidelity of that data stream. When sailors used the stars, their tools were their own eyes and a sextant. They knew the sources of error. They could account for them. In this new digital ocean, the sources of error are often just as invisible as the signals themselves.
And this table really illustrates the language of that digital ocean perfectly. What's so fascinating here is how each part of the radio frequency spectrum is like a specialized tool. You look down at the bottom in the very low and low frequency bands, and those really long wavelengths are perfect for older but super reliable long-range systems like LORAN-C, which use ground transmitters. Then you jump way up to VHF, very high frequency. That's line of sight, which makes it ideal for ship-to-ship communication, and AIS, the automatic identification system. And then you go way up into the super high frequency band. There you get these very short wavelengths that can carry an immense amount of detail, which is exactly what you need for a high-resolution radar trying to pick out a tiny buoy in a heavy sea. Each band's purpose is really just dictated by its physical properties, and a ship's collection of antennas has to be designed to listen across this entire spectrum.
Cromwell, you mentioned errors before, and wow, this is a perfect illustration of a really fundamental one. A digital ocean might sound poetic, Hazard, but this unseen ocean has its storms and its rogue waves too. This diagram shows a fundamental problem. You see, you have your direct signal, that's the line of sight path you want. But you also get signals that bounce off the surface of the water, or even off the ionosphere, miles above the Earth. These reflected waves travel a longer path, so they arrive at your receiver just a little bit later. This can cause what we call signal fading or multipath interference. Basically, the two signals can corrupt each other, and that creates a false position. In a busy harbor surrounded by buildings and other ships, this can be a huge problem, telling a navigator they have a few extra feet of clearance when in reality they have none. So yes, while this digital ocean is powerful, it can also be incredibly treacherous.
Petty, that is an excellent and absolutely necessary caution, Cromwell, which brings us perfectly to our next point. If the world is full of these signals and all their potential errors, how does a ship actually perceive them? How does it translate those invisible waves into tangible, useful data? Well, it does it with an array of really sophisticated digital senses, each one designed to read a very specific part of the environment.
Okay, let's start with one of the most fundamental senses, the echo sounder. It's basically the ship's way of seeing the seabed. The principle couldn't be simpler. It essentially shouts into the abyss and then listens for the echo to come back.
You know, the concept feels almost primal, but its importance just cannot be overstated. Before this, sailors used a lead line, a weighted rope to measure depth. It was slow, it was time-consuming, and it was imprecise. The echo sounder gives you a continuous, accurate reading of the water right beneath your keel. It is the single most important sensor for preventing groundings, full stop.
And now we get to the cornerstone of pretty much every system we're going to talk about today, the Global Positioning System, or GPS. It is, and this is no exaggeration, one of the most transformative maritime technologies ever developed. It gives a ship its sense of place in the world with just incredible accuracy by triangulating signals from satellites orbiting high above us. Before GPS became available to civilians in the 90s, fixing your position in the middle of the ocean might only be possible a few times a day, and your accuracy might be a few miles if you were lucky. GPS gives you that fix every single second, to within a few feet. It's just amazing.
Okay, now this looks complex, but the idea behind it is pure genius. The crucial point is how GPS gets its incredible accuracy, and it's all about timing. A satellite sends out a radio wave. That's the carrier. But on top of that wave, it layers a very complex digital pattern, a pseudo-random code. Your receiver on the ship generates the exact same code at the exact same time. By comparing how late the satellite signal is, it can measure the travel time down to the nanosecond.
And since that signal is traveling at the speed of light, measuring time is really the same as measuring distance. It's this measurement of distance to 4 or more satellites at the same time that lets the receiver pinpoint its location anywhere on Earth. The real brilliance is using those complex codes as a sort of digital stopwatch.
Exactly. That's what it all boils down to. It's not just a signal, it's a signal carrying a secret handshake in the form of a code. And the timing of that handshake is what tells you exactly where you are.
It's a beautifully elegant solution to the very, very old problem of knowing your position on the globe. But it also highlights a vulnerability. If someone can mimic that handshake, they can lie to you about where you are. And that is a point we will certainly be returning to.
And the results are just staggering. Just look at this chart. The Standard Positioning Service, SPS, that's what most of us use every day, is already accurate to within a few meters. But then you get to differential GPS, where a fixed ground station is correcting the signal, and suddenly you're getting down to sub-meter accuracy. And with survey-grade systems, you're talking about millimeters. It's phenomenal.
You're listening to OOTO TV with research by author Paul Bulow. But Hazard, while that precision is indeed impressive, a chart like this can also breed complacency. We have to remember the errors. The signal's journey through the ionosphere and troposphere can introduce delays. The satellites themselves can have tiny clock errors or drift in their orbits. These high-precision systems work because they have complex models to correct for all these errors. But an over-reliance on that number on the screen, that sub-meter accuracy, without understanding its potential for error, that is a significant operational risk.
And you've just raised the essential question, Cromwell. We have all these amazing digital senses, GPS for our position, the echo sounder for depth, the gyro for our heading, but this is just a flood of raw data. How does a human navigator possibly process all of this to make safe, effective decisions? Well, the answer lies on the modern integrated bridge, what you might call the brain of the ship.
And this is that brain laid bare. This is a block diagram for what's called an Integrated Bridge System, or IBS. Right there in the center, you have the processor. You can see all the digital senses we've been discussing feeding into it: GPS, the echo sounder, the speed log, the gyros.
Right. And the processor synthesizes all that different information and then sends it out to the various displays. It's sending position data to the ECDIS, that's the electronic chart display, so the navigator sees the ship's little icon moving across the map. It feeds heading and speed into the radar so targets can be tracked accurately. And, this is crucial, it sends course data to the automatic navigation and track-keeping system, which in turn controls the autopilot. It's the central nervous system, connecting perception to action. It takes a fire hose of data and turns it into real situational awareness.
And this is what all that integration enables for the user. It makes the really complex act of voyage planning incredibly intuitive. Instead of manually plotting points on a paper chart with dividers and parallel rulers, the navigator can just pull up a route from a database or create a brand new one just by clicking on the electronic chart to set their waypoints. And the system automates all the tedious calculations. You can input your desired arrival time, and the system instantly calculates the speed you need for each leg of the journey. Then, you can review the whole plan visually, checking for hazards, shallow waters, or traffic separation schemes. It completely transforms what was a laborious, time-consuming task into a streamlined, strategic process. It frees up the navigator's mental capacity to actually, watch the water. You know, Cromwell, this right here is the perfect illustration of modern system design. On the left, you have the user interface for the autopilot. It's clean, it's logical, it's designed to be used under pressure. It's a fantastic piece of user-focused engineering. But that brings up the big question, the one we really have to ask. How can these complex marine navigation and piloting systems really provide a high-quality experience for the user?
And that is the critical question, Hazard. The high-quality experience starts with that simple interface on the left, but it's guaranteed by the immense complexity you see on the right. That diagram shows the CPU, the sensor interfaces, the converters, the alarms, the redundant power supplies, the whole works. A quality experience means that when the navigator presses a button, the system responds instantly and correctly. But it also means that if a sensor fails, the system detects it, sounds a clear alarm, explains the problem, and then fails gracefully without ever endangering the vessel. The quality is in the reliability of that complex web, not just the simplicity of the control panel.
And that very concept of reliability and failure brings us directly to the future. Because as these systems become more complex and more interconnected, we face a completely new generation of risks. But at the very same time, this technology is opening the door to revolutionary new possibilities. We are charting a course right between these new threats and new horizons.
Let's start with the threats. For decades now, we've built our entire global navigation infrastructure on the assumption that the GPS signal is true. But what if it isn't? What if the position displayed on that beautiful integrated bridge is a deliberate fabrication? This is the very real threat of GPS spoofing.
And this isn't just theoretical. There was that now famous incident in the Black Sea back in 2017, where over 20 ships all at once started reporting their GPS positions miles inland at an airport. Their systems were being fed a powerful false signal, and the navigators on their bridges were completely and dangerously confused.
And this quote from Captain MacArthur of the Institute of Marine Engineering, Science and Technology really puts the danger in stark terms. This is not just some technical glitch. A bad actor could transmit a fake GPS signal to trick a vessel's navigation system, slowly feeding it false position data to drive it off course. The crew on the bridge might see their ship following the planned route on the ECDIS perfectly, while in the real world, they're sailing straight towards a reef.
Just like Captain MacArthur says, a single compromised vessel could cause a catastrophe on the scale of the Ever Given incident, blocking a critical waterway like the Suez Canal and causing billions upon billions of dollars in economic damage. It's a strategic threat to global security, plain and simple.
But for every threat, there's a corresponding horizon of opportunity. And the biggest one right now has to be autonomy. This isn't science fiction anymore. It is already happening. The Yara Birkeland, a fully autonomous container ship, has been operating in Norway since 2020. And the expert consensus is that this is going to be a gradual process. By 2025, we'll see more remote-controlled vessels in coastal areas. And by 2030, this could be a widespread reality.
The promise is incredible. We're talking about huge gains in efficiency, fuel savings, and potentially safety by removing the element of human error, which is still a factor in the vast majority of maritime incidents. But it also presents a completely new set of challenges for the requirements of these systems.
And this is where it gets really, really interesting, Cromwell. This leads to a key question. Can we connect these autonomous systems to next-gen networks like Starlink? Just imagine an autonomous vessel having instantaneous access to massive databases, downloading chart updates, live weather data, and communicating with every other ship in real time. It could make the requirement specification for these tools a living document that literally updates itself constantly.
The potential is undeniable, Hazard. However, every new connection is a new vulnerability. The more data pathways we open up to the ship's brain, the more doors we open for those who would want to compromise it. The cybersecurity challenge for a connected, autonomous fleet is immense. The very system that provides you with real-time weather updates could also be the vector for a malicious attack.
You've both just perfectly framed our final section here. To navigate between the threat of spoofing and the promise of autonomy, to build these incredibly complex systems safely, we have to be absolutely rigorous in how we define their requirements. We have to lay the foundation before we even think about building the skyscraper.
So the crucial point is this. The requirement specification for any of these advanced navigation tools must be built on 3 core pillars. This has to be a clearly defined step-by-step process. First, you have audience needs. Is the system for a highly trained officer on a supertanker, or is it for a recreational sailor on a weekend? The interface, the level of automation, all of it has to match the user's skill. Second, technical requirements. This is the nuts and bolts, processing speed, sensor accuracy, display resolution, and that reliability we keep talking about. Does it need to be accurate to a meter or a centimeter? And third, safety regulations. The system has to comply with a huge web of international standards from bodies like the IMO and local maritime laws, and those dictate everything from what information has to be displayed to how alarms have to sound.
And Cromwell's point about regulations leads to another really critical insight. The requirements for these navigation tools are highly variable. They change based on the region, the vessel's size and type, local laws, weather, and even tradition. You're listening to OOTO-TV with research by author Paul Bulow. And that last point, tradition, is one that's often overlooked. In some regions, there are unwritten rules of the road or specific channels used by local traffic that aren't on any official chart. A well-designed system has to be flexible enough to account for these nuances. The specifications for a small fishing boat in the calm Mediterranean are going to be completely different from those for a massive LNG carrier navigating the icy, traffic-dense North Atlantic. It is absolutely not a one-size-fits-all solution.
And all of this has to be built on a foundation of data. A modern navigation system's requirements have to specify that it incorporates existing databases, charts, maps, noting passages, obstacles, depths, traffic, weather, all of it. But it's not static. It also has to update that map in real time using data from the ship's own sensors, GPS, depth, speed, all while factoring in the desired course and ETA. It's a living, breathing data ecosystem. Precisely, and that's exactly why the requirements for these tools must be constantly updated and evaluated. This fault logic diagram is a perfect example. It's a plan for when things go wrong. Every time a new fault is discovered in the field, every time a regulation changes, this chart and the system's core requirements must be updated. It is a continuous, ongoing process of improvement. So, Cromwell, considering all of this, what are the key elements for a requirement specification for marine navigation and piloting tool? The key elements, Hazard, are synthesis and foresight. You must synthesize the three pillars: the user's needs, the technical capabilities, and the regulatory framework. You must account for all the variables of the vessel and its environment. And you must design for continuous evolution, with robust systems for maintenance, for updates, and for fault correction. It has to be a holistic, living document that is just as dynamic as the ocean itself.
And that brings us to our final thought. We are successfully defining the requirements for the technology. We're building systems that can sense, think, and act with incredible sophistication. But as we hand over more and more control from the human to the machine, from the bridge to the algorithm, we face a much deeper question. As our ships become autonomous, who or what is ultimately the captain?
Is it the AI making the split-second decision in a potential collision? Is it the remote operator thousands of miles away in a control center? Or is it the programmer who wrote the ethical subroutines months earlier? The technology is advancing at an incredible pace, but the fundamental questions of command, responsibility, and control, those are the new uncharted waters we are only just beginning to navigate.
Thank you for joining our investigation here on OTO TV.